Welcome to today's session. In this video, we'll dive into problem number 1629, titled Slowest Key. We'll analyze the problem, explore various approaches, and determine the most efficient solution. Let's get started. The problem asks us to determine which key was pressed for the longest duration during a sequence of key presses. We are given two inputs, a string called keys pressed, where each character represents a key that was pressed, and a list of integers called release times, where each value specifies the time when the corresponding key was released. The duration for which a key was pressed can be calculated by subtracting the release time of the previous key from the current key's release time. If two or more keys have the same longest duration, we return the lexicographically largest key among them. For example, if B and C have the same duration, we return C because C comes later alphabetically. The inputs consist of a list of integers for release times and a string for keys pressed, and the output is a single character representing the key with the slowest release time. This ensures we focus on both the duration and the alphabetical order when ties occur. Let's look at the first example to understand the problem better. Here, the release times are 9, 29, 49, 50, and the keys pressed string is CBCD. We calculate the duration of each key press as follows. The first key C has a duration of 9 since it starts at time 0. The second key B has a duration of 20, calculated as 29 to 9. The third key C also has a duration of 20, calculated as 49 to 29. Finally, the fourth key D has a duration of just 1, calculated as 50 to 49. Out of these durations, the longest is 20, and since both B and C have this duration, we select C because it is lexicographically larger than B. Thus, the answer for this example is C. In the second example, the release times are 12, 23, 36, 46, 62, and keys pressed is SPUTA. The first key S has a duration of 12 because it starts at time 0. The second key P has a duration of 11, calculated as 23 to 12. The third key U has a duration of 13, calculated as 36 to 23. The fourth key D has a duration of 10, calculated as 46 to 36. Lastly, the fifth key A has the longest duration of 16, calculated as 62 to 46. Since it is the only key with the longest duration, it is the result. Therefore, the output for this example is A. To summarize, the constraints of the problem ensure that the lengths of release times and keys pressed are the same, with at least one key press and at most 10,000. The release times are strictly increasing, meaning there are no simultaneous key presses. Additionally, the keys are always lowercase English letters. For edge cases, if there's only one key press, that key is the answer. If all keys have the same duration, the lexicographically largest key is returned. Finally, the solution must handle large inputs efficiently when n reaches the upper limit of 10,000, ensuring our approach is both optimal and scalable. When considering different approaches for this problem, one option is the brute force method. The main intuition here is to calculate the duration for each key press by iterating through the release times array and finding the difference between consecutive release times. For the first key, the duration is simply its release time since there's no prior key. During this process, we keep track of the maximum duration encountered and the corresponding key. The time complexity for this approach is O(n), as it requires a single iteration through the release times array, and the space complexity is O(1), since no additional storage is needed. However, while this method is simple to implement, it comes with trade-offs. For instance, introducing additional constraints, such as sorting for tie-breaking, can make the approach inefficient. This makes it less ideal for handling larger inputs or more complex variations of the problem. A more efficient solution is the optimized approach, which improves upon the brute force method by integrating tie-breaking logic directly into the main iteration. The idea is to simultaneously calculate the duration of each key press and determine the slowest key in a single pass through the release times array. To do this, we start by initializing the maximum duration using the first key's duration and setting the slowest key to the first key. As we iterate through the array, we calculate the duration of each subsequent key by subtracting the release time of the previous key. If the current duration is greater than the maximum duration, we update both the maximum duration and the slowest key. In cases where the current duration is equal to the maximum duration, we update the slowest key only if the current key is lexicographically larger. At the end of the iteration, we return the slowest key. This approach is efficient, with a time complexity of O(n) and a space complexity of O(1), as it avoids unnecessary operations like sorting while handling tie-breaking seamlessly. The optimized solution stands out due to its ability to determine the slowest key efficiently by considering both the duration of the key press and lexicographical order in case of ties. Sorting the data is unnecessary because the tie-breaking logic is integrated into the single iteration, which makes the approach both clean and efficient. One key advantage of this method is that it naturally handles edge cases, such as ties between keys, without requiring additional computations. After evaluating both approaches, the optimized solution was chosen for its balance of simplicity and efficiency. It achieves the same time complexity as the brute force method, O(n), but avoids the potential inefficiencies and lack of clarity that come with extending the brute force approach. By using constant space and integrating all necessary logic into a single iteration, the optimized method is the most practical and robust strategy for solving this problem. To solve the slowest key problem, we need to determine which key was pressed for the longest duration based on the given inputs. The release times array tells us when each key press ends, while the keys press string indicates which key was pressed during each interval. Our goal is to calculate the duration of each key press, then identify the key with the longest duration. If multiple keys share the same duration, we will return the one with the lexicographically larger value. To begin, we initialize two variables, max_duration, which will keep track of the longest duration encountered, starting with a value of 0, and result_key, which will store the corresponding key, starting as an empty string. Next, we iterate through the keys in keys pressed to compute their durations. For any key at index I, the duration is calculated as the difference between the release time at I and the release time at I1, provided I is greater than 0. For the very first key, when I equals 0, the duration is simply the release time at index 0, as there is no prior key pressed to compare with. Once we calculate the duration for a specific key, we compare it with the current max_duration. If the newly computed duration is greater than max_duration, we update max_duration to this new value and set result_key to the current key. If the duration matches max_duration, we then compare the current key with result_key lexicographically. If the current key is larger, we update result_key to the current key. After processing all keys in this manner, the value stored in result_key will represent the key with the longest duration or, in the case of ties, the lexicographically largest key. Finally, we return result_key as our result. This approach is efficient because it processes the input arrays in a single pass, making the time complexity O(n), where n is the number of keys. The space complexity is O(1), as we only use a few variables to track the current maximum duration and the associated key. The algorithm primarily relies on the release times array to calculate durations and the keys press string to determine the corresponding key. It's important to handle edge cases as well. For example, if only one key is pressed, the result is straightforwardly that key. If multiple keys are pressed for the same duration, the lexicographical comparison ensures we choose the largest key. Lastly, the problem assumes valid input, so we don't need to worry about empty arrays or strings. Let's now consider an example to understand how this algorithm works in practice. Suppose we're given release times equals 9, 29, 49, 50, and keys pressed equals CBCD. For this input, we calculate the durations and update our variables step by step. Starting with the first key, C, its duration is simply 9, as it's the first key. We update max_duration to 9 and result_key to C. Next, for the second key, B, the duration is 29 minus 9, which is 20. Since 20 is greater than the current max_duration, we update max_duration to 20 and result_key to B. For the third key, C, the duration is 49 minus 29, which is also 20. While the duration matches the current max_duration, the key C is lexicographically larger than B, so we update result_key to C. Finally, for the fourth key, D, the duration is 50 minus 49, which is 1. Since this is less than the current max_duration, no updates are made. At the end of the iteration, the result is result_key equals C. The algorithm efficiently identifies C as the key with the longest press duration. The time complexity remains O(n), and the space complexity is O(1). This solution addresses the LeetCode problem number 1629, slowest key, which involves determining the key that was held down the longest during a sequence of key presses. If two keys share the same maximum duration, the lexicographically largest key is returned. We begin by initializing max_duration to the duration of the first key, computed as release times, 0, and slowest_key to the first key in keys pressed. This sets our baseline for the longest duration and its associated key. Next, we iterate through the release times list starting from index 1. For each key press, we calculate the duration as the difference between the current and previous release times I, release times I1. We then check two conditions. If the current duration exceeds max_duration, we update max_duration to this new value and set slowest_key to the current key, keys pressed, I. If the duration equals max_duration, we compare the current key lexicographically with the current slowest_key. If the current key is larger, we update slowest_key. This ensures that the key with the longest duration, or, in the case of ties, the lexicographically largest key, is tracked. Finally, after processing all key presses, we return the slowest_key as the result. This implementation has a time complexity of O(n), where n is the length of the release times list, as we iterate through the list once. It is efficient and handles all edge cases, such as ties or single key presses, effectively. This is the Java implementation of the slowest key problem from LeetCode. The logic mirrors the Python solution, but Java requires explicit type declarations and uses charat to access specific characters in a string. The function calculates the duration of each key press and determines the slowest key based on duration and lexicographical order for ties. To solve this problem, we start by understanding the inputs and the goal. The release times array contains the times at which each key was released, while the keys pressed string represents the sequence of keys pressed. Our task is to determine which key was held down the longest. If two keys are tied for the longest duration, we return the one that is lexicographically larger. Let's look at an example. Here, the release times array is 9, 29, 49, 50, and keys pressed is CBCD. Initially, we set max_duration to the first key's duration, which is release times, 0, giving us 9. The corresponding slowest_key is the first key, C. Now, we iterate through the remaining keys, starting with I equals 1, where we calculate the duration for the second key as release times, 1, release times, 0, which is 20. This duration is greater than the current max_duration of 9, so we update max_duration to 20 and slowest_key to B. Next, for I equals 2, we calculate the duration of the third key as release times, 2, release times, 1, which also equals 20. Since this duration is equal to the current max_duration, we compare the keys lexicographically. The current key, C, is larger than B, so we update slowest_key to C. For the last key, at I equals 3, the duration is calculated as release times, 3, release times, 2, which is 1. This is less than the current max_duration of 20, so no updates are made. The final slowest_key for this example is C. In another example, we consider the inputs release times equals 12, 23, 36, 46, and keys pressed equals SPQR. Here, we initialize max_duration to 12, corresponding to the first key, S. Now, we calculate the duration for the second key at I equals 1 as release times, 1, release times, 0, which is 11. Since 11 is less than the current max_duration of 12, no updates are made. Moving to I equals 2, the duration is calculated as release times, 2, release times, 1, which is 13. This is greater than the current max_duration, so we update max_duration to 13 and slowest_key to P. For the fourth key, at I equals 3, the duration is computed as release times, 3, release times, 2, which is 10. Since 10 is less than the current max_duration, no updates are made. Thus, the final slowest_key for this example is P. Next, we examine a simpler case where there's only one key press. In this example, the inputs are release times equals 15 and keys pressed equals Z. Since there's only one key, the duration is simply the value of release times, 0, which is 15. The slowest underscore key is the only key pressed, Z. Therefore, the result in this case is Z. This example demonstrates the simplest scenario, where no iteration is necessary, and the output is directly determined from the input. To summarize the solution, the key steps involve computing the duration for each key by subtracting the previous release time from the current one. We then compare this duration with the current max underscore duration. If the new duration is greater, we update both max underscore duration and slowest underscore key. In the case of a tie, we compare the keys lexicographically to determine the larger one. Finally, the result is the slowest underscore key with the longest duration or the lexicographically largest key in the event of a tie. This step-by-step approach ensures we efficiently find the correct key for any input. The time complexity of this solution is O(n), where n is the length of the input array release times. First, we initialize max underscore duration and slowest underscore key with the values of release times, 0, and keys pressed, 0. This step is a simple assignment and takes constant time, O(1). Next, we enter a loop that iterates through the indices from 1 to n1 in the release times array. For each index, we perform a few constant time operations. We calculate the duration of the current key press using subtraction, compare this duration to the current max underscore duration, and conditionally update max underscore duration and slowest underscore key if the new duration is greater. Since the loop runs n1 times and each operation inside it is O(1), the overall complexity of the loop is O(n). Finally, the return statement, which simply returns the value of slowest underscore key, is another O(1) operation. When we combine these steps O(1) for initialization, O(n) for the loop, and O(1) for the return, we arrive at a total time complexity of O(n). Even when we consider different scenarios, the time complexity remains O(n). In the best case, such as when all durations and release times are identical, the loop still executes n1 iterations, making the complexity O(n). For the average case, the same n1 iterations are required, so the complexity is again O(n). And in the worst case, where all durations are distinct, the loop still needs to process every key press, which results in O(n). Now, shifting to space complexity, the solution is extremely efficient, requiring only O(1) additional space. This is because the algorithm uses a fixed amount of memory, regardless of the size of the input. The input arrays, release times and keys pressed, are not modified directly, so their storage does not contribute to additional space. Instead, the solution relies on a constant number of variables, max underscore duration, slowest underscore key, and the loop index I. These variables require a fixed and predictable amount of memory. Since the number of variables remains constant and no additional data structures such as lists or dictionaries are used, the space complexity is O(1). To better understand the efficiency of this approach, let's compare it with a brute force or naive solution. In a naive approach, we might calculate the duration of each key press and store these durations in a separate list or dictionary. While this is straightforward, it would require O(n) space to store the durations and O(n) time to compute them. Additionally, we would need another O(n) time to find the maximum duration, resulting in an overall time complexity of O(n) plus O(n) equals O(n). Compared to this, the current solution is significantly more space efficient. By calculating and comparing durations on the fly within a single pass, it eliminates the need for auxiliary storage while still maintaining the same time complexity of O(n). To conclude, let's justify the big O notation mathematically. The loop iterates n1 times, and each iteration involves constant time operations such as subtraction, comparison, and conditional assignment. This gives a total time complexity of O(n1), which simplifies to O(n) for large N. On the space side, the algorithm only uses a fixed number of variables, like max underscore duration and slowest underscore key, and does not allocate any additional memory for data structures. This ensures that the space complexity remains constant at O(1). In summary, this solution is optimal in both time and space complexity for the problem, achieving O(n) time with O(1) space, making it both efficient and elegant. One common mistake when solving this problem is confusing release times with press times. It's important to remember that the problem requires you to calculate the difference between consecutive release times, not the press times. If you mix these up, you'll end up with incorrect durations, which will throw off your solution. Another area where errors can occur is failing to handle edge cases. For example, what happens if there's only one key press? Or if two keys are pressed simultaneously or for very short durations? Ignoring these scenarios can lead to runtime errors or incorrect outputs. Additionally, large inputs are a common challenge. If you use a brute force method with nested loops to calculate durations, your solution could end up with n² complexity, which is computationally expensive and inefficient for larger inputs. Instead, you'll want to aim for a single-pass solution to keep things efficient. Another frequent issue is incorrectly updating the maximum duration. You might forget to check for ties or fail to store the lexicographically smallest key when two keys have the same duration. This is problematic because the problem explicitly states that, in the case of ties, the smaller key alphabetically should be chosen. Skipping this condition will result in the wrong output. It's also important to pay attention to the input constraints. For instance, the problem guarantees valid key presses between N and Z, but making assumptions about input validity without validation can still lead to unexpected behavior. Always be mindful of these constraints to ensure your solution works as intended. Recognizing patterns is crucial for solving this problem effectively. At its core, this is a variation of sliding window or difference-based problems, where you calculate differences between consecutive elements. The optimal approach involves using a single pass to calculate press durations while maintaining the maximum duration and the corresponding key. This ensures an O-N solution, which is both efficient and scalable. When working on this problem in an interview, it's a good idea to clarify the requirements with the interviewer, especially edge cases like ties or scenarios with only one key press. Additionally, you can demonstrate your understanding by testing your solution on both small and large inputs. This shows that you've accounted for correctness and efficiency. Finally, interviewers appreciate when you think beyond brute force methods, so always aim for the most optimal solution whenever possible. This problem shares similarities with several other LeetCode problems, and exploring these can deepen your understanding of the underlying concepts. For example, LeetCode 1047, remove all adjacent duplicates in string, involves string manipulation and windowing, which are relevant here. Similarly, LeetCode 1209 builds on this concept by introducing additional constraints, requiring you to maintain state between consecutive elements. LeetCode 424, longest repeating character replacement, focuses on finding the longest substring under certain constraints, which ties in with duration calculations. Finally, LeetCode 1769, minimum number of operations to move all balls to each box, is another difference-based problem that emphasizes efficient computation. Studying these related problems can help you recognize patterns and apply similar techniques to solve variations. There are several approaches to solving this problem, each with its own trade-offs. A brute force method involves comparing each key's press duration individually by iterating through all release times, resulting in n² complexity. While this approach is simple to implement, it's inefficient for large inputs. A more optimal approach uses a single loop to calculate press durations and simultaneously maintain the maximum duration in corresponding key, achieving O(n) complexity. This method is highly efficient but requires careful handling of edge cases, such as ties. Another alternative is to use auxiliary data structures like a hash map or list to store durations for easier comparisons later. While this increases space complexity slightly, it can simplify debugging and make the logic more intuitive. Choosing the right approach depends on the constraints and requirements of the problem you're solving. Great work! We've successfully solved the slowest key problem and reviewed the key takeaways. Remember, practice is key to mastering these concepts. If you enjoyed this video, please like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!